Hi everyone, welcome to the channel. Today we'll be looking at this problem called coin change. And since this problem revolves around coin, please let me know and comment down in the video below what is your favorite coin. If you'd like to see similar content, please click the red subscribe button on the bottom right. Alright, so in this problem we're given coins of different denominations and a total amount of money called amount, and we want to write a function to compute the fewest number of coins that we need to make up that amount. And if that amount of money cannot be made up, then we return -1. So here we see we have 1, 2, 5, and the amount is 11. So if we take the coin 5 twice, we'd have a total of 10, and then we take the coin denomination 1, and now we have 11. So if we, in this case, if we had coins of 2, or a denomination of 2 and the amount is 3, if we take the coin once, it's 2, take it twice, it's 4. There's no way that we could reach the amount 3, so we return -1. And we can assume that there's infinite number of each kind of coin. Alright, so the main idea for this problem is that we can use dp, and our dp relation will be dp of I is equal to the minimum, since we want the minimum number of coins, of dp of I, and dp of I minus denomination of the coin. So the definition of dp of I will be, since whenever we do dynamic programming, we need to state our recurrence relation. The above is the recurrence relation, and now we define what is dp of I actually. And so dp of I represents the minimum number of coins to make ith amount. So when we have something like amount is 11, then we have dp array. These are the indices. And we see our denominations. Well, here's our input. Because the amount is 11, we want the dp array to go up to I equals 11. And initially, our coins, what we know is that the denominations themselves, 1, 2, and 5, each of them will be at a value of 1. The minimum number that it takes to, minimum number of coins to reach those denominations is 1, because you just take one of the coins from the denomination. And our dp array we fill going from left to right. At each indice, we check every single denomination, as you see here, I minus denomination. And the reason why we do that is we check to see if we can use the current denomination. Let's say the denomination is 1. So if we're at, let's say, I equals 2, then we look at, if I equals 2, then we go through all the denominations. So we would do I equals 2 minus 1. And dp of I, then we would take the minimum of that. Now the thing is, when we take dp of 2 minus 1, we have to add 1 because we are using the coin denomination of 1. We're using one more coin. So this recurrence relation needs to be fixed with the +1. At each dp of I is the minimum of dp of I, which is the current cached result of the minimum number of coins, and then we check with the current denomination. And because we're using the current denomination, we have to add 1, indicating that we're using one of the coins. And the minus denomination checks that if our value I equals 4, and then our denomination is 2, then we look for I minus 2, because the minimum number of coins to make I equals 2, and then you add 2, which is taking the current coin, will equal the denomination minimum number of ways to make a value of 4. So if we continue, then if we're on I equals 3, well, we could go back to this one. So dp of 2 minus 1, dp of 1 is 1, 1 plus 1 is 2, so minimum of 2, and dp of 2 will be 1. So what that meant is this part is saying if we take one of the minimum for I equals 1, which is 1, and then we take another denomination of 1, that would be 2. Is that smaller than just taking one coin of denomination 2? And the answer is no. So that's why dp of 2 remains at 1. And we do the same thing for the other denominations, 2 and 5. But the thing is, 2 and 5 we don't check, because when you're on I equals 2, and then you subtract by 2, you're at dp of 0. And the number of ways to make 0 is 0. And then similarly for 5, we would be at dp of negative 3, because I equals 2, and the denominator is 5, so we would not be checking those. So if we proceed, we go on to 3. We have 3, and then so we would initialize dp array with float infinite. That way any of the possible values from our dp will be smaller, and they will be updated accordingly. And so the first denomination is 1, so we look at dp of 2, and we add 1, so that would be 2. And this is infinite, so initialized at infinite, so now it goes back to 2. And then we can also look at dp of 2, or denomination is 2. So dp of 1, and we add 1, which is 2, versus infinite, so it's still there. And then dp of 5 is out of bounds. Then we continue, go to dp of 4. First one, dp of 4 is initialized to infinite, so we're taking the minimum of infinite and 4 minus 1, which is 3. So dp of 3, which is 2, so 2 plus 1 is 3. Task is changed to 3. And then the next thing is we check dp minus 2, so that's dp of 2, which is 2 plus 1, which is 3, so that's still, 4 still remains at 3. And we cannot check dp of 5 because it's less than or equal to 0. So now we have 5 minus 1. dp of 5 is not infinite like the other ones, it's already been initialized to 1. And dp of 4 is 3. When we add 1, we get 4, so dp of 5 is still smaller. And we know the other ones will not be greater. We see dp 5 minus 2, dp of 3, right? Minus 2 is dp of 3, and that's 2. 2 plus 1 is 3, which is not smaller than 1. And yeah, so we could proceed to dp of 6. Help out with the notation a bit. And yeah, so we have dp of 6, which is infinite currently, and then dp of 5, which is 1, plus 1, which is 2, so that's smaller, and so we will update this. And then we have dp of minus 2, which is dp of 4. So that's 3, that's now smaller than 2. And then 5, dp of 1, which is 1 plus 1, 2. So that is the smallest. And then we go to 7. Minus 1, we have dp of 6 plus 1, so the smallest is 3. And then when we do dp of 7 minus 2, which is dp of 5, we have 1 plus 1, which is 2, and that is smaller, so this gets updated to 2. And then dp of 2, yeah, that's also 2. Now we move on to I equals 8. Once we're on I equals 8, a minus 1 dp of 7 plus 1, so that will be a 3. And then we do I minus 2 dp of 6, 2 plus 1 is also 3. And if we do minus 5, we go to dp of 3. So yeah, 3 is the smallest we can do. Makes sense because it's 1 plus 2 plus 5. And now we move on to I equals 9. Once we're on I equals 9, dp of 9 initially is infinite, and then dp of 8 plus 1, which is 4. And then minus 2, dp of 7, which is at 2, plus 1, which is 3. So 3 gets updated. Yeah. And then dp of 4 is 3 plus 1. Okay, that's bigger. So now we go on to I equals 10. So I have dp of 9, which is 3 plus 1, so that goes up to 4. And then dp of 2, which is dp of 8, or 10 minus 2 is 8, which is 3, 3 plus 1, also 4. And then dp of minus 5, 10 minus 5 is 5, and that's 1, so we have 2. And now we move on to the last one, which is 11. And so dp of 11 minus 1, that's dp of 10. So that's 2 plus 1, which is 3. And then dp of 11 minus 2, dp of 9, 3 plus 1, that's not smaller than 3, so we don't update. And then dp of 6, which is 2 plus 1, also 3. So we see our final answer is right here, 3 coins. And we see that when we have something, well, let's see that case, dp of 2, because the amount is 3, it would be up to here. And everything would be infinite. Doing example 2 right now, everything will be infinite, initialized, and then we'll update 2 to 1. And because once we get onto indice 3, we look at, when I equals 3, we look at dp of 3 minus 2, which is 1, and that's infinite. So we would not be updating that. So when we see infinite, we would return negative 1. dp of amount equals infinite. All right. Now we could talk about if there are any cases. And so one case is if the amount equals 0, then return 0, because there's no ways to make, there's zero number of ways to make the amount 0. And then the other thing is we need to initialize an array equal to amount plus 1 length to infinite float if. Because we're using minimum, so if we initialize everything to infinite, once we make a possible combination of coins, then it will be updated in our DP array. Now the next thing is to initialize all single denominations to 1. That's right here where we have coins 1, 2, 5, and then we put a 1 on 1 and 1 on 2 and 1 on 5, meaning that there's one way to make coin of denomination 1 and one way to make coin denomination of 2 and one way to make coin denomination of 5. Well, one way, and 1 is the minimum number of coins needed to make that amount. Then we apply DP recurrence relation fill up array. That's this stuff here that we were doing. Well, this stuff, which is also this stuff. And then we return DP of amount if it is less than infinite. Return -1 if not infinite. Alright, so here we go. First one, if amount equals 0, return 0. Now we initialize our DP array. We say DP equals float infinite. And we want to make this length amount plus 1. Now initialize all the denoms, so we'll go denom in coins, iterate through all the coins, and then if denom less than length of DP, you want to make sure that the denomination, so if our length is 11, right, and then we had a denomination like 12, it wouldn't be able to be in the array, so we would get out of bounds. So be careful for that. And denom equals 1. Then we apply our recursive relation, so we do it for I in range, and we'll start with 1 because 0 has 0 number of ways to make 0, so there's no purpose to look at that. And we go through the length of DP, doing all the elements, and then we have to look back for each denom for the recurrence relation. That's right here. We need each of these denoms, so we go through all the denoms and the coins. Want to make sure when we subtract I minus denom that it's greater than or equal to 1. Otherwise, there's no reason to update because the index is out of bounds, or we might be looking at 0, and as we talked about before, there's no purpose to look at 0. DP of I equals minimum DP of I, meaning the current minimum number of coins to make the amount is already minimum, or we use the current denomination, add 1 because we're using the coin, it might be better. Now we check DP amount because this caches the minimum number of ways to minimum number of coins to make the amount, and if it's less than infinite, then we return that amount. The other case is that it's not less than infinite, so we return -1, meaning it's not possible to make the amount. Alright, so let's clean this up. We don't need this anymore. Let's run to see if it's going to work. Alright, looks good for that. Let's submit, see if it's... Alright, great. Looks like it's submit. Let's talk about runtime and space complexity. So the space complexity for this algorithm is O of n, and n is number, let's go back to the problem so we can see this, is number of, is amount. And this is O of n space because of our DP array right here. It's amount plus 1, so it's basically n. And then runtime, we have n amount D for the coin denominations. And we see here we're going through O of D for that for loop, and then we have I in range n, or it goes through the length of dp, and then it goes to denom, so it's n times d, and overall runtime is n times d. Big O notation, we ignore what the smaller factors are. So the overall runtime is O of n times d, and the space complexity is O of n. And that's everything for today. Thank you guys so much for sticking around to the end. If you like the video and you learned something and have fun, please click the like button, the thumbs up on the bottom of the video, and click the red subscribe button on the bottom right to be notified of similar content. And yeah, follow me on social media. It's in the link below. And share this with anyone else that you think is fun. And don't forget, leave a comment about what your favorite coin is. Thank you so much, and I hope you guys all enjoy the rest of your day.